Hello guys, today we want to start the second lecture of transform calculus and partial differential equation. So in this lecture we want to talk about integration by part, and then we solve one example because we need it for finding Laplace transform of some functions. Then we solve some other examples. So we start with Laplace transform of a ramp function ft equal to t. Then we find Laplace transform of a sinusoidal function, so it's ft equal to sine t. And at the end, you will find Laplace transform of t to the power of n. So let's start with integration by part. So imagine you have two functions like u, which is a function of x, and v, which is function of x. So we have two functions, u and v are function of x, and let's say we want to find the derivative of u times v. So if you want to find derivative of u times v, so we have d over dx of u times v. So it's equal to, you know that it's equal to u times dv over dx plus v times du over dx. Now if I integrate from both sides of equation, so we have the integral of d over dx of u times v. So I take integral with respect to x is equal to, I have to take integral from right hand side of equation as well. So we have integral of u dv over dx with respect to x plus the integral of v du dx times dx. So from the left hand side of equation, if I just cancel dx, so here I cancel dx with dx here, and right hand side dx goes with dx. I cancel out this dx with this dx. So we have the integral of duv. So integral of duv is equal to u times v is equal to the integral of u dv plus integral of v du. As a result, I can say that integral of u dv is equal to uv minus integral of v du. So this equation is equations of integration by parts. Now we solve one example to see how we have to apply equation of integration by part to solve some examples. So the first example. In this example, we want to find the integration of x times cosine x dx from 0 to pi over 2. So the first step in solving this integral, if you want to use integration by parts, so we have to choose u and v dv from this integral. So in this example, I assume that x is equal to u, and I assume that the rest, which is cosine x dx, is equal to dv. If x is equal to u, dx, I can take derivative of both sides of equation, so dx is equal to du. And if we have dv is equal to cosine x dx, so I can take integral from both sides of equations. As a result, v is equal to sine x. In fact, I just took integral from right hand side of equation, so it ended up with v, and left hand side of equation, so the integral of cosine dx is equal to sine x. So now we have u and v. So based on the integration by parts, so integration by parts says that the integral of u dv is equal to u times v minus integral of v du. As a result, so we have integration of, so u is x, dv we said is cosine x dx. It's the integral that we have here. So from the limit of integral is 0 to pi over 2. So it's from 0 to pi over 2. It's equal to, so based on definition, u times v, u we have it, it's x, and the v we found it, it's sine x. So we have to apply limit of integral is from 0 to pi over 2 minus integral from 0 to pi over 2. So here we have v, so v is sine x, and du we already found it is equal to dx. So now I have to find this term. I have to apply upper limit, which is pi over 2, lower limit, which is 0. So for this case, if I apply upper limit, so we have pi over 2 sine pi over 2, sine pi over 2 is 1. As a result, we have it's equal to, if I apply upper limit is pi over 2 minus lower limit. Lower limit is, if I apply 0, so we have 0 times sine 0 is 0, so it's minus 0 minus the integral of sine x is what is minus cosine x, and we have to apply lower limit and upper limit, so we have minus pi, or we have 0 from pi over 2, so it's equal to, if I apply pi over 2 upper limit, so it's equal to 0, and if I apply lower limit is equal to 1. So from here we have pi over 2 minus times minus is plus, so here we have minus, here we have minus, so it's plus. If I apply upper limit, so we have cosine pi over 2, which is 0, and if I apply the lower limit, so we have cosine 0 is 1. As a result, the integral is equal to pi over 2 minus 1. So we could easily find integration of x times cosine x dx from 0 to pi over 2 by integration by part. So choosing u and dv is very, very important. If you choose a wrong one, so maybe you never end up with the solution, or you make your solution very complicated. For example, let's say I say here second solution. And in the second solution, I assume that, for example, u is, cosine x is equal to u, and x dx is equal to dv. From here we have, if I take derivative of both sides, so we have minus sine x dx is equal to du. And if I take derivative, integral of both sides of the equation here, so in the left hand side we have half x squared is equal to v. So if I continue the solution, as a result, the integral of x cosine x dx from 0 to pi over 2 is equal to u times v. So u here we have is cosine x, and v is equal to times half x squared from 0 to pi over 2 minus integral v du. So v is half x squared and du is sine x dx. So integral from 0 to pi over 2. So if you look at this integral, we wanted to solve the integral of x cosine x dx, but we ended up with half x squared sine x dx. So it's another integral that we cannot solve it. So we have to use integration by part. As a result, in this case, we can see that by choosing u equal to cosine x and dv equal to x dx, we never end up with this solution. So if you want to have the solution, as you can see on top, so we have to have x equal to u and v equal to sine x. As a result, we can say that the second solution doesn't work. So this solution doesn't work and we have to go with the first solution. So now I just wanted to refresh your memory about integration by part. Now we will be back to Laplace transform of finding Laplace transform of ramp function. So in this example, we want to find Laplace transform of ramp function. So it's ft equal to t. If you want to find Laplace transform of function, I already said that we have to apply a definition of Laplace transform. So we have Laplace transform of t is equal to, based on definition, the integral from 0 to infinity e to the power of minus st ft dt. So if I plug ft in the equation, so ft is equal to t. As a result, we have the integral from 0 to infinity t e to the power of minus st dt. So in order to solve this integral, we have to use integration by part. So in this case, I assume that t is equal to u. As a result, dt is equal to du. And I assume that e to the power of minus st dt is equal to dv. So as a result, v is equal to minus 1 over s e to the power of minus st. Now we have u and v. We can find Laplace transform of t, which is equal to this integral, the integral from 0 to infinity t to the power t times e to the power of minus st. So it's equal to u times v. So u, we already had it. So it's it's t. And v here we found it is minus 1 over s. So it's times minus 1 over s e to the power of minus st. We have to apply upper and lower limits of integral minus integral from 0 to infinity v du. So we found v is equal to minus 1 over s e to the power of minus st, and du is equal to dt. It's equal to. So we have, at first I have to find, let me close here. So at first we have to find these terms. So I have to apply upper limit and lower limit. What happens if I apply upper limit? So what's t times minus 1 over s e to the power of minus st when t approaches to infinity? So let's find it. So we say note limit of t times minus 1 over s e to the power of minus st when t approach to infinity. So we have, in fact, minus t in numerator and in denominator. So we have e to the power of negative. I can put it in denominator with power of positive. So it's e to the power of st when t approaches infinity. So in this case, we have infinity in numerator, we have infinity in denominator. In order to solve it, I use L'Hopital rule. So based on L'Hopital rule, so we can say it's equal to, so I have to use L'Hopital. I have to take derivative of numerator, which is minus 1, over derivative of denominator, so it's s squared e to the power of st when t approaches infinity. So now we have 1 over infinity is equal to 0. And it's for upper limit of these terms. So if I apply the lower limit, so we have 0. So 0 times e to the power of 0. So it's equal to 0. As a result, this term is equal to 0. So Laplace transform of t is equal to, we have minus here is plus, so it's 1 over s. The integral from 0 to infinity, e to the power of minus st dt. So now we can easily find the integral from 0 to infinity of e to the power of minus st. So it's equal to, here we have 1 over s. Integral of e to the power of minus st is minus 1 over s e to the power of minus st. So the integral from 0 to infinity. So we have, I can just take minus 1 over s out. So it's minus 1 over s squared. If we apply the upper limits, we have e to the power of minus infinity. And if I apply lower limit, we have e to the power of 0. E to the power of minus infinity is equal to 0. As a result, we have minus 1 over s squared times minus 1 is 1 over s squared. So we can say that Laplace transform of t is equal to 1 over s squared. So we could easily find Laplace transform of this function, ramp function. Now we solve another example. In this example, we want to find Laplace transform of ft equal to sine t. Again, for finding Laplace transform of this function, what we have to do, we have to use the definition. So we have Laplace transform of sine t is equal to integral from 0 to infinity e to the power of minus st. ft here is sine t, so sine t dt. So in order to solve this integral, so we have to use integration by part. In order to simplify the equation, I call this integral at a capital because I want to use it later. So in order to solve this integral, we have to find u and v. So because we have to solve it by integration by parts, so I assume that u is equal to e to the power of minus st. As a result, no. So here I have to, I consider u as sine t. As a result, du is equal to cosine t. And I assume that dv is equal to e to the power of minus st times dt is equal to dv. As a result, v is equal to minus 1 over s e to the power of minus st. So a, which is the Laplace transform of sine t, or is equal to this integral, is equal to u times v. So u is sine t and v is minus 1 over s e to the power of minus st. I have to apply the lower limit and upper limit, minus integral from 0 to infinity v du. So v is minus 1 over s e to the power of minus st, and du is cosine t. So sorry, here when we have u is sine t, du is cosine t dt. So times dt. Now we have to apply the lower limit and upper limit here. If t approaches to infinity, we have sine infinity. Sine is always between minus 1 and 1. But here we have e to the power of minus infinity. As a result, if I apply the upper limit, so this term is equal to 0. And if I apply the lower limit, so we have sine 0 is 0 and e to the power of 0 is 1. So 0 times 1 is 0. As a result, this term is equal to 0. So it's equal to minus times minus is plus. We have 1 over s squared, no, 1 over s, the integral from 0 to infinity, e to the power of minus st cosine t dt. So now we have to find this integral, the integral of 0 to infinity e to the power of minus st cosine t. So here you can see again, in order to solve this integral, we have to use integration by part. So I call integral from 0 to infinity e to the power of minus st cosine t dt as b capital. So just call it b because I want to simplify the solution, and I find this integral. So in order to solve it, we have to find u and v again. So I assume that the cosine t is equal to u. As a result, minus sine t dt is equal to du, and I assume that e to the power of minus st dt is equal to dv. As a result, v is equal to minus 1 over s e to the power of minus st. So b is equal to b capital, this integral is equal to u times v. What's u? U, we have it is cosine t times v. V is minus 1 over s e to the power of minus st from 0 to infinity, minus integral from 0 to infinity v du. So v, here we have it, it's minus 1 over s e to the power of minus st, and the du is minus sine t dt. It's equal to. So let's find this part. So if we apply the upper limit, cosine infinity is between minus 1 and 1, it's limited. E to the power of minus infinity is 0. If I apply the lower limit, so we have cosine 0 is 1, e to the power of 0 is 1. So as a result, we have 1 over s. and so it's equal to 1 over s. So here we have minus times minus is plus. The integral from 0 to infinity plus 1 over s. So let me write it plus 1 over s, integral from 0, the integral from 0, my integral is so ugly, let me just, to be honest, it's very difficult to work with these pens, and so I'm so beginner. So 1 over s, the integral from 0 to infinity, e to the power of minus st sine t dt. Okay, just let me check this sign. Here we have minus times minus is plus. Oh, we have another minus here. As a result, this one should be minus. So so as a result, we ended up with b equal to 1 over s minus 1 over s. So what's this integral? The integral from 0 to infinity e to the power of minus st sine t. So here on top, we define it as a capital. So if you see here this integral 0 to infinity e to the power of minus st sine t dt. So it's equal to a. As a result, it's equal to a. Here we have one equation. We had another equation in this part. So here we said a is equal to 1 over s times this integral. We already called this integral as b. So as a result, here we have another equation. So it's a equal to 1 over s times b. So now we have two equations, two unknowns. We can easily solve it. So we have two equations. The first equation says that a is equal to 1 over s times b. And the second equation says that b is equal to 1 over s minus 1 over s times a. If we solve these two equations, we can easily find a, because our goal is to find a. A is Laplace transform of sine t. So if I want to find a, so we have I just instead of b, I say it's equal to, here we have a is equal to 1 over s times b. As a result, b is equal to s times a. So s times a, I pick that from this equation, is equal to 1 over s minus 1 over s times a. So we have, I just bring a to the left hand side of the equation. We have s plus 1 over s times a is equal to 1 over s. As a result, so we have s squared plus 1 times a is equal to 1 over s. I can cancel this s and this s. So we will end up with a is equal to 1 over s squared plus 1. In fact, a, at the beginning we defined it's equal to Laplace transform of sine t. So we could easily find Laplace transform of sine t using this equation. In fact, Laplace transform of sine t is equal to 1 over s squared plus 1. So in general, we can say that Laplace transform of sine kt. K is a constant, is 1, 2, 3, anything. It's equal to k divided by s squared plus k squared. So for example, here we found Laplace transform of sine t, k was equal to 1. As a result, Laplace transform is 1 over s squared plus 1. And we can do the same procedure for finding Laplace transform of cosine kt. So cosine kt is equal to s divided by s squared plus k squared. So we could find Laplace transform of trigonometric functions sine kt and cosine kt. Let's go through the next example. In this example, we want to find Laplace transform of ft equal to t to the power of n. So first of all, we have to know that n can be 1, 2, 3, and etc. So in order to find Laplace transform, what we have to do, so we have to use definition. So we have Laplace transform of t to the power of n is equal to the integral from 0 to infinity e to the power of minus st. ft here is t to the power of n dt. So how we can solve this integral? So here we have t to the power of n. We have to use integration by part to solve this integral, but depending on n, for example, if you have n to the power of 10, so we have to do integration by part 10 times to end up with the solution, and it takes a long time. So as a result, we can say that Laplace transform of t to the power of n is equal to n factorial divided by s to the power of n plus 1. For example, Laplace transform of t, we already found it. We said is equal to 1 over s squared. So t to the power of 1, so we have 1 factorial is 1, divided by s to the power of 1 plus 1 is s squared. So we already had it. Or let's say you want to find Laplace transform of t to the power of 10. So it's equal to 10 factorial. So 10 factorial is 10 times 9 times 8 times 7 times up to 1, divided by s to the power of 10 plus 1 is 11. So that's enough for this lecture. In the next lecture, I'm going to talk about sufficient conditions for the functions to have Laplace transform.